Oh yeah, you're in. Very long. Yeah, I think you were the ones that have 11.
Okay, so yesterday we started, or 2 days ago, we started talking about how to calculate the area of a parallelogram which is spanned by two vectors, which means that if you have two vectors v and w, and that forms some parallelogram, we would like to know its area. And we found a very simple formula for calculating the area, and that is the magnitude of v cross w is equal to the area of this parallelogram. And that was this formula right over here. And then the second formula that we saw is, in order to find the area of a triangle, you just take half of the magnitude of v cross w. So let's do an example, and then we're going to come back to this other thing, parallelepiped. But first, they say take v to be this and w to be this. Calculate the area of the parallelogram spanned by v and w. Okay, so our v over here is equal to 145, and our w is equal to -2, -1, 2, -2, -1, and 2. So what is v cross w? V cross w is going to be the determinant of the matrix I, J, K, 1, 4, 5, -2, -1, and 2, which is equal to so we go I times the determinant of 4, 5, -1, and 2, minus J times the determinant of 1, 5, -2, and 2, plus K times the determinant of 1, 4, -2, -1. So far, so good? Okay, and then this is equal to so in our first component, we're going to have 8 minus -5, which is +5. In our second component, we're going to have negative of 2 minus 10, which is plus 10. And then our third component, we're going to have -1 plus 8, which is 13, -12, and 7. Okay, so 13, -12, and 7. Any questions so far? Okay, so once we get our cross product, in order to find the area of the parallelogram, so we know area of the parallelogram is going to be the square root, or let me first do, is the magnitude of V cross W, which is the square root of 13 squared plus 12 squared plus 7 squared. They tell us that that is 19, or approximately 19. Approximately 19. So that's the area of our parallelogram with the vectors V and W. So it's the area of this thing. Now, if we wanted to find the area of the triangle with these same vectors, so just this over here, well, we know the formula. The area of the triangle is equal to 1/2 times the magnitude of V cross W, which is approximately 19/2. Any questions so far? Okay, another thing that they want you to be able to do is find the area of a parallelepiped. So a parallelepiped is created by 3 vectors, V, W, and U. And they use this notion, they call it a scalar triple product, but you actually don't have to know this at all. What you should instead remember is what a determinant is for a normal matrix. That's what we want to actually remember. So if I have 3 vectors that create a parallelepiped, let's say it's U, V, and W, and they create some type of, okay, not drawn great, but a parallelepiped. Then the area of this parallelepiped is going to be the determinant so the area of this is going to be equal to the determinant of the matrix with U on the first row, so U1, U2, and U3. So we imagine U is equal to U1, U2, and U3. V is equal to V1, V2, and V3. And W is equal to W1, W2, and W3. So if we have these 3 vectors, then the area spanned of the parallelepiped spanned by these 3 vectors is the determinant where you put U on the first row. One second. So you put U on your first row, that's here, V on your second row, and W on your third row. And you just take the determinant of that matrix. So again, this is the matrix U1, U2, U3, V1, V2, V3, and W1, W2, and W3. Any questions about this? Yeah.
How do you decide given the three vectors and equations?
So it actually doesn't matter because so for some reason, yeah, for you take the absolute value. So you don't only take, and in general, the same thing holds for the parallelogram. Because you're taking the magnitude of the cross product, it doesn't matter which one goes first and which one goes second. The only difference between the vectors going on top or below is with this sign. So we know that V cross W we know that this is equal to negative W. Okay, let me start anew. So we know that V cross W is equal to negative W cross V, which means that the magnitude V cross W is equal to the magnitude of W cross V. Which means in this case, it does not matter if V is the second row, right? You definitely have I, J, and K in the first row, but it doesn't matter if V is in the second row or W is in the second row. And similarly with our parallelepiped, we're really looking at the absolute value of the determinant of the matrix U1, U2, U3, V1, V2, V3, W1, W2, W3. So it doesn't matter which one goes on top and which one goes on the bottom. If you know some linear algebra, you know that if you flip these rows, every time you flip one, so let's say you move this here, you get a negative for the original determinant. If you flip these, you get a negative, or so on. Okay, so for our parallelepiped, this is the formula. You don't need to remember that. That's the scalar product. You should remember the second part, V is equal to the magnitude of the determinant of U, V, W. Any questions? Okay, so the second part of this question asks us to find the volume of the parallelepiped in figure 12. So that has these two vectors. And then the third vector is this vector 0, 0, 6. So my guess is they're using the trailer skipple, the triple scalar product right over here. But because I don't want to talk about what that is, I'm just going to take the determinant of this whole thing. Okay. So again, our V here is equal to 145, 145. Our W is equal to -2, -1, and 2. -2, -1, and 2. And our, let's say, U is going to be equal to 0, 0, 6. So please take a couple of minutes and try to find the volume of the parallelepiped spanned by V, W, and U. Okay, so we know that this is the determinant, the absolute value of the determinant of 1, 4, 5, -2, -1, and 2. So actually, in order to simplify this, I'm going to put the first vector on top, 0, 0, 6, 1, 4, 5, -2, -1, 2. Which is a good trick to know, because we're going to be taking the coefficients of the thing on top, might as well want 0 and 0 to appear as often as possible. So this determinant is going to be the absolute value. So I'm going to ignore that for a second. Let's just take the determinant. So I'll erase this for a second. 0 times the matrix, and then it doesn't matter what goes in here, minus 0 times the matrix, doesn't matter what goes in here, plus 6 times the matrix, 1, 4, -2, -1, which is equal to 6 times -1 plus 8. So 6 times 7, which is 42. Any questions about this? Yeah.
So you said the order, like of the, permanent matrix, like it doesn't matter, like the rows.
Yeah, it doesn't matter because you're taking the absolute value. So let me just write something quickly, but if you take linear algebra, you'll see this a little more clearly. The determinant of, let's say, the matrix A1, A2, A3, B1, B2, B3, C1, C2, C3 is equal to negative times the determinant of B1, B2, B3, A1, A2, A3, C1, C2, and C3. So if you flip the rows, you just get a negative. And so if you take the absolute value, they're the same. So it doesn't matter where this row appears. Any other questions? Okay. So in general, even in R2, meaning you don't have to be in R3, you can also compute now areas of parallelograms and triangles spanned by just vectors in R2, V1, V2, W1, W2. Now you might think, well, I don't really have, how can I take the cross product if I need, let's say I have two vectors, but I need to start with I, J, for example, but then I only have two values, V1 and V2, W1 and W2. Well, what's the determinant of this thing? And the answer is there isn't a determinant for this the way it's written. So you just have to add a component. So you imagine that you go to 3 dimensions, you add a K, and then what will the components be in the K dimension? Well, 0 and 0. There are no components in the Z dimension. And then you just take the determinant. So if you have these vectors V and W in R2, then you can think about the cross product as being this, where you just add zeros to your third dimension. And it so happens to be because that for I, when we take this cross product, you take the I, and then you get 2 zeros from here. But that gives you 0. So this disappears. The ith part disappears. Same thing with the jth part. The jth part looks at the matrix that comes out of here, V1, W1, 0, 0. Well, that also disappears because of those 2 zeros. And so you only really get your kth component. And the kth component looks at the matrix that's formed by erasing this row and this column. So it's this matrix over here. V1, V2, W1, W2. Well, that's when I take this determinant and I put a K here, but I'm of course taking the magnitude of this. That's the same as just taking the determinant of my two vectors. So V was equal to V1, V2, and W is equal to W1, W2. So that's V1, V2, W1, W2. Now you don't have to remember this. You can always just put together your cross product, but you can also remember this. And this will just tell you that if you're in 2 dimensions and you want to find the magnitude of the area of the parallelogram spanned by 2 vectors in 2 dimensions, you just take the determinant of those 2 vectors. So it's pretty clear that determinants first are very important for area, and second are easy to use, again, to find area. You can now do a lot of problems that would have been a little harder to do. And now if you just have the components of your vector, you can immediately compute these parallelograms, or I think personally, most importantly, the triangles. I think computing areas of triangles is a little more important than areas of parallelograms, but parallelograms happen to also be very important. So they ask us to compute the area of this parallelogram over here in 2D. So this is V is equal to 1, 4. V is equal to 1, 4. W is equal to 3, 2. So the area of this parallelogram is going to be the absolute value, and I'm going to ignore that for a second, the determinant of 1, 4, 3, 2, which is equal to 2 minus 12, which is equal to negative 10. But now we put an absolute value on our negative 10. And because area has to be positive, we get 10. And that's this solution over here. Any questions? Okay. So here they prove some stuff about the cross products. I'm not going to focus on proofs in this class. So we will continue with the summary. So once again, it's important to remember what the determinant of a 2x2 matrix is. It's the building block for all of this. In fact, if you ever need to take a determinant of a 4x4 matrix, you end up reducing it to the determinant of a 3x3 matrix in the same way that a 3x3 matrix is reduced to a determinant of a 2x2 matrix. So you go, and again, this is a little bit more important in linear algebra, but still, if you have a 4x4 matrix, A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4, D1, D2, D3, and D4. And you want to compute this determinant. Well, that's going to be, you go to your A1, you put that here, A1, times the determinant of the 3x3 matrix. That happens again by crossing out this row and this column. So B2, B3, B4, C2, C3, C4, D2, D3, and D4, minus, because every time you move, you get minus, then the next one, and now you put A2. Do the same thing. then plus A3, do the same thing. And then minus A4. So again, you get a minus. They alternate. Do the same thing. Now you have these 3 by 3 matrices. How do you compute them? Well, you go to the 2 by 2 matrices. So you compute each one of them by boiling it down to 2 dimensions, and then you go to 1 dimension, or 1 by 1 matrices, which is just numbers. So it's important to know how to compute, and you can do this for 5 by 5 and so on. So it's important to know how to compute 2 by 2 matrices. And in this class, we will not have to do 4 by 4 matrices. 3 by 3 is the most we are going to do, which is convenient because computing a 4 by 4 matrix takes a long time. To do a 3 by 3 matrix, we know the strategy. We put these coefficients. Remember to put a negative here. And then when we compute the cross product, we do the same thing. So we imagine that these are your A1 and your A2 and so on. And we put them as coefficients over here, and we compute the 2 by 2 matrices. Then some important facts about the cross product. So by far, the most important property is that V cross W is orthogonal to both V and to W. And we proved that. And it will be used very often in this class. So very important to remember. The second most important property, which actually won't appear that much, but gives rise to the property that cross products compute area, right? Sine plays the role as height. It kind of does what y does, and y is the height. So if we want to compute areas of parallelograms, we need to know the height. And so that's why this second property is also very important to remember, and is very similar to the property that we saw with cosines. V dot W is equal to the magnitude of V times the magnitude of W times cosine of theta. Now, this one is more important because it's one that we use directly to compute angles. And so it's much more important to remember it. But it is also important to remember that cross products are connected with sine, and that because of that, we can use it to compute areas. And that's another important thing about cross product. They're used to compute areas. We also saw the right-hand system. So how to know if you have V over here and W over here? How do you know if your vector is pointing up or down? Well, you put your index fingers in the direction of V, the back of your hand in the direction of W, and you see in which direction your thumb is pointing. So I would say that these properties, the most important one, again, is that V cross W is orthogonal to V and W. The second one is this thing about area. And then you have these other two properties, the sine one and the right-hand rule. Now, with regard to these properties, the most important one is this one. V cross W is equal to negative V cross W. And it's very easy to remember because you're either going in one direction or in the other direction. You're either going up or you're going down. So not hard to remember that property. The second one is the second most important one, which is that if the two vectors are parallel, your cross product is 0. Though I probably would prefer to find the angle between them and see that the angle is 0. That's my personal preference. And then the last two properties you don't actually need to remember and are not really used. With regard to these properties, well, actually pretty easy to remember using the right-hand system. So you only really need to remember the right-hand system, and you can figure all of this out on your own. And then, like we said, cross products are used to find the area of a parallelogram spanned by V and W. So I would say that this is after the fact that V cross W are perpendicular. The second most important property about a cross product is that it can be used to find the area of parallelograms, or it can be used to find the area of triangles. Then we saw this fact about determinants, that if you want to find the area of a parallelepiped, you use the determinant. And that's all we have for cross products. Any questions? Okay, so I posted the new homework. I'm going to try to also update some of the Achieve homeworks, and then I'm going to try to post another homework that will be a little different than the homeworks that I've been posting. And those questions will come. They'll be very similar to these type of textbook questions. Compute the cross product, find angles, and so on and so forth. So a little just more computational to make sure that you're practicing these type of computations. Okay. So something like this, just calculate cross products or find areas. Okay. So now that we know something about the cross product, we can move on to the next topic, which is planes. And we will see that planes are very important for multivariable calculus, because the same way that in one-dimensional calculus, we use lines, we calculate the tangent lines to curves. So let's say you have some function. Here's your function, and someone asks you to calculate the tangent line at this point. Well, this point, we should be able to do that, and we can find a line that's tangent to this point. Well, similarly, in multidimensional calculus, we're not looking for lines that are tangent to points, but rather we will be looking for planes that are tangent to points of our surfaces. So let's say our surface is some dome. At a given point, we won't be asked for a line tangent to that point, because there are many lines that are tangent to that point. You can take a line and rotate it. You can take a line tangent to the point and rotate it, and you'll still get lines that are tangent to that point. So instead of looking for lines, we are going to be looking for planes that are tangent to this point. Here's a plane, so it's called the tangent plane. And that's why planes are so important for multidimensional calculus. So a plane we will see is going to be characterized by an equation that looks something like this: ax plus by plus cz is equal to d. So this is kind of similar to lines. For lines, we had something like y, or let's say ax plus by is equal to c, right? This characterizes a line. And generally, if we're finding the slope, we put the y on the other side, and the c is the y-intercept, and we divide by b. But this, of course, is an equation of a line. So similarly, we would want to be able to find the equation of a plane. And for an equation of the plane, we just add another coefficient to our z dimension, and we still have this constant. But instead of c, we just use d to simplify things. And we will see that the coefficients in front of x, y, and z, you can create a vector out of them, a, b, c. And this is called the normal vector. To our plane. And what that means is, if this is our plane, and it's characterized by the equation, the set of all points x, y, and z, such that ax plus by plus cz is equal to d, then you can think about a vector pointing directly out of this plane, orthogonal or perpendicular or normal. There are kind of three ways of saying perpendicular in math, I guess, to all the vectors in the plane, which means if I take any vector in the plane, let's say this vector over here, then the angle between these is 90 degrees. And any plane has two vectors like this, one pointing up and one pointing down. And that vector, if you think about it, can characterize your plane. As long as you know this one vector, you can find the plane where all the vectors in the plane are perpendicular to that vector. And this is the vector ABC. That's this vector over here. So in fact, the very nice thing about planes is that these coefficients can be used directly to find a single vector, and this vector characterizes your entire plane. It tells you what your plane is. So that's a very nice fact. Any questions? Okay. So that's given over here, and in this picture, your normal vector, we generally denote it by n. Your n is equal to ABC. So n is equal to ABC. And your plane that goes up. So the normal vector alone will actually not give you all the information that you need for your plane, because you can have planes that are parallel to each other with the same normal vector, right? If I have a plane, I can have a normal vector sticking out of it, but I can also shift the plane and still have the same normal vector. So what you need is you need two pieces of information. You need a point that this plane passes through, and you only need one, and then you need a normal vector. And once you have this point and your normal vector, you have your plane. And this point is what gives you your last coefficient. The point P gives you this coefficient. Why is that? Because we would like, if your P0 is equal to x0, y0, and z0, and you're given your normal vector a, b, and c, then you can find this equation. You can find this equation. Okay. So again, if you have your point P, so we can imagine the P0 is this point right over here. Then now we can find D, and you have your normal vector. So you have these two pieces of information, N, which is ABC, and P0, which is A0, B0, and C0. then you can write this equation over here, and you can say, well, A times x0, one second. So x0, y0, z0. So A times x0 plus y times b0 plus c times z0 is equal to d. And that will tell you what your d is. Yeah, well, you can flip them, yeah. Oh, b, y0. And that will tell you what your d is. So for example, if I tell you, okay, my normal vector is the vector 1, 1, 2. And a point that passes through the plane, let's say the point is 0, 1, 1. Find the equation of the plane. So what you end up doing is you go, okay, I know that the general equation of my plane looks something like x, right? A, which is 1 times x, plus b, which is 1 times y, plus 2z is equal to d. So I almost have all the information that I need. I have my x, my a, well, I don't have my x, but I have my a, my b, and my c. Now, what is d? Well, in order to find d, you just plug in this point into the equation. So you can say, okay, I know that 0 plus 1 plus 2 times 1 is equal to d, which means the d is equal to 3. So now I can say that my plane is x plus y plus 2z is equal to 3. And that gives me the equation of the plane that I was looking for. Any questions about this?
Explain quickly why it's 2z.
Yeah, so the coefficient for your c, this is your c and your normal vector, 2.
Oh,
So you put that here.
yeah.
Any other questions? Yeah.
So like what exactly does d represent?
So D represents so different points get you give me a second. I believe I think it represents the distance from the origin, the shortest distance from your origin to the plane. I believe that's what it represents. So if your plane goes through 0, 0, 0, your D is 0, right? Because your x is 0 plus 0 plus 0. Yeah. Any other questions? Okay. So let's try another example. And we will see how to get the normal vector using cross products. So in order to find planes, a fundamental tool is cross products. Because if you know two vectors in your plane, so if I have a plane and I have two vectors that I know in it. So let's say this is one vector, v, and this is another vector, w. So these are two vectors that lie in the plane. How can I find the normal vector to this plane? Any ideas? Yeah. Yep, you just take the cross product, and we know that the cross product is orthogonal to both v and w. So it must be your normal vector to your plane. So n will be v cross w. So that's why cross products are so important, because that ultimately, when we look for a tangent plane, what we're really going to be looking for is this normal vector. And we'll see how we would be getting it. So let's do one more example. Let's imagine that my normal vector, so we imagine we have the normal vector, and it's the vector, let's say 3, 1, 0. And then I have a point. Let's say this is the point 1, 2. Let's go 1, 0, 2. Take a couple of minutes and try to find the equation of the plane that goes through that point and has that normal vector. So we know that the equation of our plane should be something like 3x plus y plus 0 is equal to d. So now we just need to find d. So this tells us 3 times 1 plus 0 plus 0 is equal to d. So the equation of our plane will be 3x plus y is equal to 3. And this looks like a line, but it isn't. In 3 dimensions, the z is now restricted. So the z goes in every direction. So this is in fact a plane. Okay, and we're going to stop here.